Where do you go to learn the art of printed circuit board design?
Everybody recognizes that you have to continually grow. It's kind of like in Alice in Wonderland. Alice is in the red forest. In this forest, you have to run faster and faster just to stay in the same place. And I think that encapsulates where the industry is today. You need to be able to grow on your own, to learn on your own, take advantage of opportunities like what you have here at AltiumLive.
This is what it means to be a great PCB designer. You understand signal integrity, you understand fields and waves, you understand digital electronics and high-speed signaling, you understand the limitations and risks of design trade-offs, you understand simulation, you understand scripting and customization so you can squeeze more juice out of the tools that you have.
If we build a community, it really makes a foundation for ways we can come together in a more personal way. Designers could find new fabricators, or a new assembly, or a new source, or a new mentor.
They love to look at what other people are doing and then imagine what they could do with that as the basis and combine that with ideas they get from all over the place so that they can make wise decisions in the design process.
We see what you make, and it's awesome.
It's my sincere pleasure to welcome everybody to AltiumLive, your AltiumLive. This is something that we started 3 years ago, and the first one we spooled up in 6 weeks, and we ended up having, I think, about 120 of you guys show up. And it's really become something special, and I think that last night, the reception that we had, for me, was very special. And not because it was entertaining, although it was. For me, what was remarkable was the connection that the two individuals that brought that here had and what really connected them together. Did anybody here have a chance to talk to Brockett, the musician, and or Dave Starkey, the guy that designed the electronics? Can we bring the house lights up just a bit? It's hard for me to see the audience. For me, what was remarkable, if you spoke to them, these two individuals were really starkly different individuals. Really different guys. But if you watch the way they interacted with each other and the way they were almost sort of predicting each other's moves, at one point Dave was removing one of the fascias from the piano, and Brockett just kept playing. It is as though they had done that a million times, although I don't know if they did. But what was remarkable to me was the connection that they had. And the connection that they had was they're both artists. They're both artists that express themselves in different ways. And the thing that connected them together was that device, was that musical instrument. And that musical instrument, very much to me anyway, had a soul. And that's really what attracted me to this profession to begin with. And I suspect that that's what attracted many, many of you. I know I've talked to Carl about it, and he very much takes a lot of pleasure in seeing the things he creates being used in the public and affecting people's lives. How many people were here last year? How many people have been here all 3 years? Okay, good, so my material will be fresh. I always like to tell stories. I think those that have seen us before would know that. But I think it tells the story of what you guys have helped us create. So I got two stories. So the first one was when we got here the first night, we were unloading the U-Haul, and there was a gentleman there just outside, and he says, "Are you guys with Altium?" I said, yeah, we are with Altium. Oh, he says, "I'm one of your biggest fans. One of your biggest fans." Oh, awesome, we'd like to hear that. What's your story? And he says, "Well, I'm a design engineer, and I had been outsourcing layouts, and I just came to the conclusion that I should start doing my own layouts as a consultant." And I said, "Okay, well, how did you settle on Altium Designer?" And he said, "Simple. You called me back." The second story I'll tell is one I'm actually quite proud of. So I was walking through the hall this afternoon, or excuse me, last night, and I saw a gentleman I recognized. And he recognized me, and he says, hey, Lawrence, how you doing? And I walked up, and I put my hand out, and as I did, he put his hand out, and he was about to introduce himself. He was going to give me his name. And I said, no, it's nice to see you, Kelly. Thanks for coming. Now, Kelly was an individual I sold as a salesperson a license to, it must have been 11 years ago. Went to his facility. But what struck me about that interaction was he instead of shaking my hand, he said, thank you for remembering my name, and gave me a hug. And the reason I tell these two stories is because that is really the hallmark of what we've really built with all of you guys in the room, is that connection between us and the individual, and AltiumLive is just a manifestation of that. Now, what that's created is Altium Designer now is the #1 most used professional printed circuit board design product on the planet. Well, thank you very much. However, that applause really should be coming the other direction, because overwhelmingly, you guys have created that, because you are passionate about what you do, and this is just a vehicle. Altium Designer and the other products we make is just your vehicle for expression. And you guys make these decisions. And without all of you in the room, we would, quite frankly, we would have nothing. And I was here when we had nothing. I was here when I would call and nobody knew who the heck we were. Nobody knew who we were. And that story I told about the guy who said, well, simply, you called me back. Well, I called you back because you would actually take my call. It's a true story. It's an absolutely true story. And so if we then look at what you guys have helped us build, we are the #1 product used in printed circuit board design today, and I'm very proud of that. Last year, we added just a bit north of 8,000 brand new users of Altium Designer. 8,000. And you do the math, that's 1 an hour over the course of a full year. And overwhelmingly, those products, and I'll say, it's cliche, but 99% of those transactions were done directly. They were done between one of our people and one of you guys. And very rarely, if any, did we talk to any of your bosses. Right? It was you guys making this call. So thank you very much for that. Now, this first guest, so we're going to switch it up a little this year. So we're going to bring out the first keynote. I'll come back out. We'll do a bit of housekeeping. We'll send you off to your breakouts. This first guest is really an indication of what you guys have also enabled us to achieve, because, quite frankly, he's a legend. And I say that because he's just always been there since I've been in electronics. So that's been since late 90s, 98, 99. He's just always been there. So much so that when we were preparing, I was going through his credentials because I was planning on having to introduce him, and then come to find out we made a video, so you'll get to watch the video, which is far more entertaining. This gentleman being here and participating is an indication of just how far we've come. Just how far we've come. And it's our distinct pleasure to be able to bring these individuals for your enjoyment and for your education. Really, really, truly an impressive person. As I was going through his resume, it just blew my mind. It's shocking that I didn't know all these facts before. So with that, thank you very, very much for coming to Altium Live and making it really a great event, something we're very, very proud of. And with that, I'll bring out the first video and the first speaker. Thank you very much.
Eric Bogerton is the Dean of the Teledyne LaCroix Signal Integrity Academy at bethesignal.com. He is also an adjunct professor at the University of Colorado, Boulder, in the Electrical, Computer, and Energy Engineering Department. Eric received his Bachelor of Science in Physics from MIT and master's and doctoral degrees in physics from the University of Arizona in Tucson, and has held senior engineering and management positions at Bell Labs, Raychem, Sun Microsystems, Ansoft, and interconnect devices. He has written some of the most successful technical books on signal and power integrity, and is one of our industry's most influential teachers on signal integrity worldwide. Eric and his wife Susan founded Bogerton Enterprises in 1990, which was acquired by Teledyne LaCroix in 2011. Since concluding his live public classes in 2013, he has devoted his efforts into creating the Signal Integrity Academy, a web portal offering all his classes and training content online. Ladies and gentlemen, please welcome Eric Bogerton.
Well, good morning, and I really want to thank Lawrence and Judy and Sarah for inviting me to join you guys today, and also for that really wonderful introduction. And thank you all for coming today as well. I want to share with you, and I call it kind of a work in progress, because I want to share with you some of the work I'm doing now, some of the research I do at University of Colorado in Boulder. And I'm sharing this partly to give you a little idea of what I'm working on, but also I'd like to get some of your feedback on it. And so after the presentation, if you can run into me later this morning, I'd like to get your reactions and some of your feedback on this. So here's what I'm working on now. You know, many of you know that I've been involved in the training education business for signal integrity, power integrity for many years. And I've gone a little around the world, and I've done a lot of training for professional engineers. And what I'm working on now is trying to translate what I have gone around and trained practicing engineers to do, to translate that into training students so that when they become practicing engineers, I don't have to go around and train them. And so I've been thinking a lot about and working on what are the important kind of broad-based skills and some specific skills I think engineers need when they start out. And really the problem I've been dealing with and what has made my company successful for many, many years is filling a need that I have found out there, and I'm sure many of you have experienced this as well, that if you look at the traditional education experience that you receive in going through some sort of post-high school education, the skills that you gain in going through traditional education just really aren't sufficient in order to train you with not so much the skill of, well, how do I design this memory circuit, or how do I design this filter, but I call it kind of the broad-based skills. And these are the ones that I think every engineer needs to be armed with to be successful. And that's part of what I want to get some of your feedback on. There are two kind of general broad-based skills that I think are really important for every engineer. The first is this idea of taking what you learn in the classroom, the principles, the essential principles of engineering, taking those principles and learning to apply them in practice. Because after all, you know, I think that, and even Lawrence said earlier, that the design process, laying out a board, there's a lot of art to it. Many of you that do board layout and board design are artists translating in your creativity into the design of boards. Well, it takes more than just being an artist designing a board, because if you take a schematic and translate the schematic to layout, you miss some important principles. A schematic tells you about connectivity. It tells you what parts you're going to use, how they connect together, but it doesn't tell you anything about noise. Once you have the connectivity correct, everything else in the design is about noise and noise control. And in order to be thinking about when you lay out the board, when you design the physical interconnects, in order to think about how do you design those physical interconnects to minimize the noise that can be created, it really requires understanding some of these essential principles in electrical engineering. It's kind of like the idea that what influences the signals on those physical interconnects is, unfortunately, ultimately, Maxwell's equations. And it's the boundary conditions of the materials and the geometry with Maxwell's equations that influence how signals are going to behave. Unfortunately, the way we teach Maxwell's equations, and certainly at CU and many other universities, is all about solving differential equations with boundary conditions and getting all these different functions out of it. And unfortunately, we oftentimes don't do a very good job of translating what do those equations mean, how do we use them in order to help influence our design decisions. So I think this is one of the important areas. I'm going to show a couple of examples of this as we go. So one of the broad-based skills I think we need to instill in our students and in engineers is this idea of how do you take what you learn in the classroom and apply it to the real world in practice. A second important broad-based skill is this idea of how to use the tools that we use correctly. And I lump into that, the three most important tools of design, simulation, measurement. And it's what are the best design practices, the best simulation practices, the best measurement practices based on our understanding of how the tools work, what's going on under the hood, and our understanding of the problems that we're trying to deal with. So these are two general areas that I think we don't train engineers enough in, and what I focus on. And I've taken these general principles and I've kind of folded them into what I consider to be the 6 most important broad-based skills that I think all engineers should have. And this is one of the areas that I'd like to get your feedback on as well sometime during the day. I try not to hide this too much with my students. And in fact, I have a number of students here today from CU. And so I'm going to embarrass you all. Students from CU, if you can stand up. Stand up. Okay, now all of you guys who have job openings, those are experienced electrical engineers to be, and you want to grab them sometime during the next day or two. They shouldn't be here tomorrow because our class is tomorrow, so I expect them back. But grab them today and then talk to them about some of your opportunities. Okay, thanks. You haven't gotten off quite so easy yet. And so what my hidden agenda is with my students is to empower them to become their own expert. And I try to instill 6 what I think are the most important broadband skills that every engineer should have. And so here's my list, and I'd love to hear what you guys might have on your list of what you think is important. And so I'm just going to go through them pretty quickly because I want to show you some examples of what I mean by these. And so the first one is this main idea we've talked about of how do you take what you learn in the classroom, apply it to the real world? How do you take advantage of that engineering foundation? The second one is rule number 9. So what I want you to do when you encounter any one of our students here in the hallway, I want you to pin them and ask them, what's rule number 9? And if they can't answer that clearly, I want you to come back and tell me, and I'm going to change their grade. Because rule number 9, I think, is one of the most important principles in engineering. And rule number 9, for those of you who have taken other classes or seen other lectures that I've done, rule number 9 is before you do a measurement or simulation, anticipate what you expect to see. It's the most important consistency test that I think every engineer should be doing on a regular basis. It helps exercise your thinking about the system. The third is the idea of principle of debugging. How do you find the most important step in debugging a product or a system is finding the root cause. How do you find that root cause, and how do you have confidence that you found the correct root cause? Because if you don't have the right root cause, the chance of fixing a problem is pure luck. And so you have to have the right root cause. And so it's a little bit of art, a little bit of skill, a little bit of experience in debugging. The third is mastering the scope. I think the oscilloscope is like I call it the Swiss Army knife of any lab. It is the most important instrument that you should have available. And I think it's really important to understand how to use it correctly, to use it to get to the answer quickly, and to minimize the artifacts in the measurements. The fourth is this idea of reverse engineering. We do that all the time. In a perfect world, all the documentation we get would be perfect and clear and pictures, and it would all be consistent with how the product and the component really works. I don't know about you guys, but I rarely find that to be the case. The documentation is either missing information, poorly documented, or it's about the previous rev, not the new rev. And so that means, I think, as a practicing engineer, you need to know how to investigate the properties of a component or a tool or a system on your own using the knowledge that you have and the tools that you have. That's reverse engineering. And it's remarkable how much you can learn about how a product really works and what its real performance is by reverse engineering. I'm going to show you a couple of examples of that. And the last is communication is so important, and it's technical communication that I think is so important. I think it's really important that all engineers take every opportunity to practice articulating the technical concepts. So these are the 6 important principles that I try to incorporate in the classes that we do. And when you encounter my students in the hallways, I want you to quiz them on these, because they should be skilled in these broad-based skills, and they can always use some practice in describing them to you. So I want you to all take the opportunity to quiz them a little bit when you see them in the hallway. Well, these are what I think are really important. This is what I try to train our students at CU. But what if you haven't taken one of my classes, or you haven't taken one of Rick Hartley's classes, or you haven't come to some of these events before? Where do you get information? Where do you get your knowledge about design principles, about the best measurement practices or best design habits? Where do you get all this information? Well, I think if you go around and survey folks that don't come to these kinds of events, they'll tell you that the most practicing engineers get their training online, right? And some of you may remember this very famous cartoon of The New Yorker when the internet was just coming out. This is in 1993. There's one dog saying, "On the internet, nobody knows you're a dog." And I think that's a really important message to keep in mind when you get information predominantly online. Because even though it's posted online, or because it's in someone else's design, or it's in your last design, doesn't necessarily mean it's a good thing to do. And even if that dog that posted it on the internet is a really smart dog, it doesn't mean that it's a good thing to do. And as I go around and I talk to engineers, and I do training classes, and I get questions from engineers, I see so many what I think of as bad habits being used. Now, I know none of you guys would ever do any of these things, but here's some of the bad habits that I see being used in the industry. And I'm not going to go through a lot of the details, because I want to show you some of the good habits. But just as a cautionary tale, things to pay attention to. It's about using scopes wrong. And I don't mean this, well, I mean this in the most loving way, but if you're a millennial and you've played a lot of video games, just keep in mind, a scope is not a video game. That there is a process to use. It's not about getting to the next level and pushing every button you can. There's a process in using a scope. So there's about using probes. It's about soldering. You know, so many folks seem to think, and I see this even among professors at CU, to solder, it must take the highest temperature so the solder melts fast. It's about designing the stack, selecting the layers incorrectly, or how power is distributed. Big one is return path design. If you've taken Rick Hartley's class, you should know how to design return paths pretty well. It's about so many misconceptions and bad habits about the use of decoupling capacitors. And the other one I see is about using copper poor. And these are just a couple of the examples that I see routinely as what I think of as bad habits. And so you say, why are they out there? Well, I think it's because many designs work in spite of these habits, not because of them. And sometimes it's hard to distinguish what is in spite of and what is because of. And part of that is because when you look at products out there, you know, I said that if you have the schematic, it tells you about connectivity. Everything after connectivity is about noise. Well, if the interconnects are transparent, in other words, if you can make your product out of a solderless breadboard with the wires going all over the place, then the interconnects, and if it works, on the solderless breadboard, the interconnects really aren't important. The electrical properties of the interconnects are not important. It is, the interconnects are transparent. And so doing something when you design the board and lay out the board and it works may be a little misleading to you, thinking, oh, it's working because I designed it this way, rather than in spite of designing it this way. And sometimes products may encounter, we sometimes refer to them as black swan events, very unusual combinations of many events happening that conspire together to give you one noticeable glitch or one noticeable problem. And these problems oftentimes are because of the combination of many noise sources adding together just at the, I hesitate to say the right time, but just at the wrong time. So they're right on top of each other, giving us enough of a glitch to cause one or oftentimes 2 bit errors at the same time, so it's not corrected in error correcting code. And so unless you look for that noise in your system, you really don't know how much noise is there. And I'm going to show you an example of, even if you try looking for it, if you're not using good measurement technique, best measurement practices, you may be misled at what you see. So I think part of the reason there are a lot of bad habits is because systems work in spite of some of these bad habits. And I'm going to show you a couple of examples of what I mean. The first one is an artifact in using a 10x probe. Now, how many of you use oscilloscopes? Everybody, right? Because it's the Swiss Army knife of every lab. I think it's an essential skill for every engineer. How many of you use 10x probes? You get 2 of them with every scope that ships, sometimes 4 of them with every scope, so they're ubiquitous in the lab, really commonly used. Great probes, but they do have a few artifacts to watch out for. Here's one of them. Actually, we'll see 2 of them. So here is the 10x probe tip, and I've got the ground lead connected across the side there. There are 2 problems in probing that can show themselves in some situations. The first problem is, if you look at that physical structure, that's the physical part of it, think of it in your mind's eye electrically. So kind of this is part of the practice of applying the classroom lessons to the real world. You want to think about that electrically. What's your mind's eye, the engineer's mind's eye, see, then you see that. And what you see is the loop inductance of the tip. You see the 9 megohm resistor in series that gives you the 10-to-1 voltage divider with the scope 1 meg. But there's also this 9.5 puff capacitor across that resistor. So the equivalent model for this probe isn't this high impedance 9 meg resistor. It's really the 9.5 puff capacitor, and we get that inductor. And so there are 2 consequences of that. One is, okay, you got an LC circuit. That's a series LC circuit. It's going to have a self-resonant frequency, and that means there's some frequency in which it has a dip, a really low impedance. And when it has that low impedance, that means a lot of signal is going to get through that frequency. And then you put in the numbers, again, apply simple principles to the physical world, and it's about 100 megahertz for this structure. That says that for signal frequency components like 100 megahertz, they're going to get through because it's not a 9 meg input impedance, it's a really low impedance, and depending on what the resistance of the source is, it can change the Q, and so you can get some oscillation. But remember that number, 100 megahertz, because that's where we're going to have the oscillation in the probe. That's problem number 1. Problem number 2, though, is when I pull the signal and return path apart and make that and do the probing on the board with the signal clip and the return clip somewhere on the board, what have I made? When I pull the signal and return far apart, I've made an antenna. And that's why we often say, you didn't mean to make an antenna. All I wanted to do was probe 2 different locations on the board. But when you pull the signal and return away, you've made an antenna, and that's why we often say there are 2 kinds of engineers, those who are designing antennas on purpose and those that are doing it not on purpose. And so we've made an antenna. And because it's an antenna, that means it can do 2 things. One is it can radiate, and the second is it can pick up. And that introduces a really important and subtle artifact as well that I think is important to pay attention to because it means that we will sometimes measure things that aren't really there. And here's the example of it. So here's a little test board. This is one of the boards, the first board that my students design. It's a little timer circuit with a hex inverter on it, simple digital circuit. And it's a little hard to see, but I'm using one of the 10x probes to measure a switching signal coming out of one of the IOs. And it's a pretty fast hex inverter. I went through the catalog and found the fastest hex inverter I could. It's about a 2 to 3 nanosecond rise time on the end. So we're using one of the probes in order to measure that switching IO. And then I've got a second probe that's literally just sitting there, not touching anything, but the tips are shorted together. So I've got a little loop. I'm going to use that second probe to measure the noise on one of the other lines, but before I do that, I just shorted the return and the tip together, and it's sitting nearby. What have I created? I've got the process of probing. I've got that 10x probe connected to the signal line, and you think, well, it's a 10x probe. It's high impedance. There's no current flowing. But it's not really a 9 meg resistor. It's a 9.5 puff capacitor. And if you look at the 100 megahertz frequency components of the signal that's switching, at 100 megahertz, that 9 puff capacitor has about 150 ohms of resistance or of impedance. That says 150 ohms, that's not much. You got a 3 volt signal that's switching, you got 100 megahertz frequency components, you're going to get, well, 3 volts and 150, you're going to get 20 milliamps of current flowing through that high impedance probe. And so we have created, in the process of doing a measurement, we have created a radiating antenna that's going to be broadcasting out to anything nearby. And now we come along with another probe and we put it nearby, and what have we just done? We've built a pickup antenna. And so without connecting that quiet probe to anything, just sitting there as though we're going to do a measurement, here's what we see. This is, the yellow is the signal at the IO that's switching, and the red is what we see on this adjacent probe, just sitting here minding its own business, shorted together, not touching anything else, just sensitive to the pickup noise. And if you look at the scale there, that's 1.5 volts of peak-to-peak noise. It's just sitting there minding its own business, but because I have current in the probe that I'm doing the measuring with, I have that 20 milliamps of current circulating at 100 megahertz, it's broadcasting and I'm picking it up through the mutual inductance with the other loop. So if you're not aware of these really fundamental principles, you may think, when I connect that probe to one of the circuits, I may think, wow, I have 1.5 volts of noise on the quiet line, when in fact it's just magnetic field pickup between the probe that's doing the measuring and the probe that has the signal on it and the probe that has the quiet line. So because of that effect, we can take advantage of it, because now we have a built-in simple field probe, a little sensor. And so we can take our 10x probe with a loop, and now we can use it to sniff out near fields on our board. And here's an example of evaluating the radiated emissions from a board with different layout techniques. This is where the principles should be applied to the artistic side of layout. This is, again, an example of one of the boards that I have my students do in the first round. This is that simple timer board, and I have 2 boards, one that they design without worrying about noise and the right way of doing layout, but just design it for connectivity. And there's another one that we give them that is designed for good layout, so it means a good continuous return path on it. Well, we're using the probe, so we're turning it on, it's running, we're getting some signals coming out of it, it's switching. We get the hex inverter switching, it's driving some LEDs there. It's also, because of the poor return paths, the large loops, it's radiating like a banshee. And we're using the 10x probe as a near-field probe to sense how much it radiates. So this is the example of the board that the students build and how much near-field pickup we have. And you can see here, so the blue is the signal coming off with a coax, so there's no radiation from, or no emissions from the measurement process because I'm using a coax on the board. That's the blue. The red is what we see picked up in the near field because of this board. And on this scale, that's 700 millivolts peak-to-peak noise just from the board itself, currents moving around on the board. When they design the board well, it's exactly the same circuit, exactly the same components, exactly the same placement. The only difference is the layout. And the layout in this case is designed with good continuous return paths. And when they do that, here's what the pickup from the board looks like. And so it's another example of the impact layout decisions have in electrical performance, even though these two boards came from exactly the same schematic with exactly the same connectivity. Well, I wanted to show one other example. This is, again, I said that once you have the connectivity correct, everything else about the board is about noise. That unfortunately, what we do in the design of the interconnects isn't going to improve the performance of the product above and beyond what the silicon or the active devices can do. All the interconnects are going to do is distort the signals, add noise to it. And so our job is really to minimize the distortion, minimize the noise that the interconnects contribute to. Well, if you don't measure the noise, if you don't have a gross failure, if you don't measure the noise, you don't know how much noise is there. And so one of the important skills is to, hey, let's evaluate how much noise do we have in our product. And I'm going to show you one example here looking at power rail noise. Now the example I have here, this is again the same board that we're going to look at. In this example I've illustrated, again, applying the principles we learn in the classroom to the real world. This is a simplified general model for power distribution. I'm not going to go through a lot of the details on it. Maybe in another AltiumLive I can come back and do a session on power delivery design and analysis. But this is a really simple example here. And in this particular case, we're going to be looking at the noise generated by the chip switching. All those IOs that are switching, I get 3 LEDs, each is about 30 milliamps of current. That's 100 milliamps of current switching. So that's that current source on the far right-hand side. That's the die that's switching that current. That current switching is going to generate noise on the die. Well, if I have voltage noise on the die, where that arrow on the right-hand side is, that's where the noise is that all the other IO on the die see. If I measure the noise on the board, in the arrow on the left, if I measure the noise on the board, what am I going to see? Because what I've built here by connecting the capacitors, the MLCC, those are the decoupling capacitors, by connecting the capacitors to the board, it is impossible to not connect them without some loop inductance in their path from the pads on the IC to the location of the capacitors on the board. And when you do that, what have I just built? If the noise is happening where the arrow on the right-hand side is, and I'm measuring where the arrow on the left-hand side is, what's between them? It's an L and a C. And what does that make? A low-pass filter. That means that any noise I see on the die, or happens on the die, if that is the source of the noise, any noise that happens on the die, in getting onto the board, has to go through this low-pass filter. And that means the high-frequency noise is going to be cut off. Now, we can measure the noise on the board. And here is an example of it. So we're going to look at right on the MLCC capacitors, and then we're going to look over where the voltage regulator module is as well. And here's the result. So we're switching a couple of the I/O, so we have a lot of switching current. The green is the I/O that's switching, so you have a trigger reference point, so you can tell when we have switching. And the yellow is what we measure on the board. And the plot on the left-hand side is the noise that we measure right at the capacitors, the decoupling capacitors, and the noise on the right is what we measure the LDO. And there is some inductance between them, and so there's another low-pass filter from the capacitors to the LDO, and you can see, hey, there's a little bit of noise difference. Not a lot. And you look at it and say, wow, that's great. Yep, I see switching noise, but it's not very much, right? And you think, great, good design, ship it, ready to go. But that's not where the noise the chip cares about. Because the noise the chip cares about is what the other I/O are going to see, because that's going to contribute to the switching noise on the die. And so we need a way of measuring not the noise on the board, but the noise on the die. And so here is a technique that, again, we try to include in all of our classes that will help us evaluate the noise on the die where we care about it. So here's our hex inverter. I got 5 of them shown here. One of them we're going to use as the trigger coming off. That's going to trigger the scope. We got 3 others that are going to be driving the LEDs, so we got a lot of switching current. And then we use 2 of the I/O as sense lines. One is pegged always low, the other one is pegged always high. The voltage that we measure coming off the board, here it is coming off the board, the voltage we measure coming off the board of the quiet low is going to be the voltage on the ground rail on the die, and the crosstalk between that signal return path and every other signal return path on the board for low. And the line that's pegged high is going to be a measure of the voltage noise on the die itself, on the power rail of the die. And so we can probe the die using some of the I/O coming off the board. Very important, very simple technique. And we just write the microcode in order to control the I/O so that there's a quiet high and a quiet low. When we do that, here's what we get. So here is, now the green is the I/O that's switching, so we can see a synchronous signal of switching noise. The scope's triggered with the I/O that's switching. The yellow is what I showed before as the voltage noise on the board, and the red is the voltage noise on the die. And I tried to use the same scale for everything so you can kind of do that comparison. And you can see that, oh my gosh, if I look at the noise on the board and that's all I pay attention to, hey, that's 50 millivolts out of 3 volts. That's nothing. That's great. I'd be proud to show that to anybody. But if we look at what's really going on the die, where it's really important for the operation of the I/Os of the die, oh my gosh, we've got 700 millivolts peak-to-peak switching noise on the die. And so it says that if noise is the important thing that we're designing for, we're adjusting the layout, it's really important to understand the artifacts and the best measurement practices in order to extract and characterize the noise in your system. Well, you look at that example and the other ones, and so I put together a list of, and kind of many of you may remember Stephen Covey. He passed away a number of years ago. He's a great, I don't know, kind of these days the term we use is hacking your life. He was all about improving the quality of your life through habits. And the first book that he wrote that really gave him nationwide attention was 7 Habits of Highly Successful People. And as kind of an homage to Stephen Covey, I put together my list of 7 habits of successful board designers. And this is specifically for 2-layer boards. There are a few other rules that will apply to multi-layer boards, but this is specifically for 2-layer, which is a lot of the IoT kind of boards, a lot of the microcontroller boards that we certainly use at CU and are popular in the industry. I wrote this up in a Signal Integrity Journal, and so you can take a look at that at your leisure. But here's the quick list, and I'm just going to go through a few of these. First habit is about using the narrowest line that your fab shop, your general fab shop can do for signals and 20 mils for power. Now, the first question everybody asks is, well, isn't 6 mils or even 5 mils, isn't that awfully narrow? And how much current can I get through a 6 mil trace? And when you look at the trace itself, I mean, it's smaller than a human hair, right? The cross-sectional area is like a quarter of what a human hair is. How much current can you possibly get through one of those lines? And don't you have to worry about the current handling capacity? And so one of the first experiments we do in our class is we blow stuff up, and I have to be a little careful. And so we use these little test boards that have different line widths on them, and we see how much current can we put through before it starts smoking. And I insist that every student wears safety glasses just in case, right? So they do the experiment. They see, how much current can you put through one of these lines before it gets warm noticeably and then starts smoking, or gets hot and then smoking. And anybody know how much current you can put through a 6 mil wide line, 1 ounce copper, before it gets even noticeably warm? What is absolutely astonishing is you can put an amp. So if you don't have a compelling reason otherwise, if you're just connecting signals around, 6 mil, even a 5 mil line is perfectly fine for the kind of currents. And how much current can you put through a 20 mil wide line before it's noticeably warm at all? You can put 3 amps. And so if your board is only using 3 amps or less, no reason not to use 20 mil wide for power distribution, and then 6 mil for a signal. It gives you the highest interconnect density, and then you use the narrow, as narrow a via as you can in order to get the high interconnect density. So the other couple of the other rules are about the layout, using the signals on one layer, continuous return path ground on the other layer. You want to adjust the placement of the parts and rotation of the parts in order to get minimum congestion, so you can do most of the routing on the first layer. But rarely, in a dense board, dense two-layer board, rarely can you get all of the routing on one layer. You have to do some cross-unders, and that's where when you do a cross-under, you want to keep them very short, so the gap in the return path is minimized. And if you can't keep it short, then you want to provide a bridge across that moat that you created in the ground plane with a ground strap. So here are a couple of examples of it. So you keep it short, number one, and when you can't do it short, add some moats or some bridges across those moats that you've created. The fifth is about the placement of decoupling capacitors, and it's all about the number one important message is you want to reduce that loop inductance because it's part of that high-pass filter, or the low-pass filter, and it's part of the creating the impedance to the capacitor. So you want to keep that loop inductance as absolutely small as you can, and that's where using power puddles, like I've shown here in the bottom example of the board, where you have short, wide connections from the decoupling capacitor to the power pads of the IC, as well as to the ground plane down below. So you keep that loop inductance low. The connectors are just as important as the other routes, and it's about maintaining return path adjacent to signal paths. And then habit 7 is there are 2 habits in particular that I find really, really, really common that I think are wrong and I think should be avoided. One of them is this myth of using 3 different capacitor values in the power distribution. And the last one is about copper poor. I think copper poor, there are rarely any compelling reasons to use copper poor. It will more often cause more problems than of any benefit. And so I recommend never using copper poor unless you can identify the strong, compelling reason. Don't think that after you design the board, you do all the routing and the connectivity, that I'll just throw copper everywhere else and that'll be good return paths. Unfortunately, it doesn't work that way. You have to engineer the return paths just as carefully as the signal paths. So these are what I think are the 7 most important habits in designing simple boards. And now I want to show you how we apply these to a real example. So the second board I have my students do is looking at an Arduino. This is a simple Arduino board. Over 1 million of these have been manufactured out there. And I think that even though, we said earlier, even though there are 1 million of these boards out there and they all work, doesn't mean that they represent good design habits. The problems in these boards, which we can easily measure, aren't always enough to cause noticeable problems, although sometimes they do, and it's just hard to know. It's a noise problem. But when you look at their designs, you realize that they have many bad habits represented in them. And I wanted to share some of them with you and show you the impact of if you design this correctly, what happens to the performance. So I have it here an example of it, and I don't mean to pick on any company, but I just grabbed offline, off the internet, an example of the layout of an Arduino Uno board. It's got the 328 microprocessor, which I'm a huge fan of. I think, is Bob Martin here from Microchip? Yeah, you're one of my heroes. I love the 328 and the other microprocessors in those families. SAMD 21 and 51 are great chips. So here's a 328 over here. It's got a little interface chip as well. So on the left, we have the layout. It's a 2-layer board. They're all 2-layer boards. And on the right, we have an actual board. This is one of the common boards that are in the industry. And I put a light behind it just so you can see. It's a 2-layer board, and you look through it, and you can see all the gaps in the planes down below. Again, this was designed as you design the connectivity, and then you pour copper on the top and the bottom, thinking, I'll throw copper at it. Copper's good, right? So it must be a good return path. And we'll see the consequence of that. So I looked at this board, and I have my students look at it as well, and we think about it in terms of the good habits, and we look to see what are being violated. And here are examples of 5 habits that I don't recommend that this design illustrates as kind of bad habits. And so one of the tests I have my students do is they look at the board, they think about the principles they've learned, and look at what was done wrong, and what will they do different in their design. So here's some of them. It's about the decoupling capacitors. Good luck finding them, where they're located or far away from where they need to be. You got large loops going there. The return path control is almost non-existent. The IOs, how many ground pins are on the Arduino board? Anybody know? 3. you got, and only one of them is on the same side of the connector pins for the 13 digital I/O. So it's greatly lacking in return connections. And then it's got the uncontrolled copper everywhere. So these are problems with this design. And so the second board project that I have my students do is they take a look at this, they measure it, they see the noise that they have. And so here's an example of what some of that noise looks like. And again, I said before how important the technique we use for probing is in influencing what we measure. And unfortunately, it's really hard to probe one of these Arduino boards, and here's what happens when you try to do just naively. So we stick a ground pin in a ground wire in the ground pin, and we measure one of the signals that's coming out. And so, of course, what have we built when we do this measurement? We built an antenna. And so when we look at when we try to probe one of the other lines to see the noise on the quiet high and quiet low, we've just built some coupled noise. And without making a connection, that is, without looking at one of the quiet high or quiet low lines, just bringing that probe nearby, we're going to see a lot of noise. And so just the act of trying to measure gives us some noise. And in this case here, that scale is 200 millivolts a division. We got, like 3 or 4, 500 millivolts peak-to-peak noise just because of the probe-to-probe pickup. So you have to be really careful when you do these measurements not to have that kind of artifact, so you see the noise on the board. And unfortunately, this board is not designed for probing, for testing, and it's not designed for low noise signals coming off because you got one digital signal, you got one return pin, and you got a whole bunch of digital signals that are switching. But you can kind of mock something up, and so we're using these really small loops with the little spring tips, and we're looking at a signal that's switching, and we're looking at some of a quiet low and quiet high, and then I needed to add some extra load to the I/O so we get more current switching out, so we see more of the switching noise. So we mock something up, and here's what you get. So we're looking at one of the I/O that's switching, and we use, because we want to have multiple simultaneous I/O switching, we use a port command so we can switch multiple I/O simultaneously, as distinct from you turn one on and then the next, it's not simultaneous switching. So we're switching 3 simultaneously here. The yellow trace that's the trigger that we're using to say, okay, now we're switching all these I/O, and then we're looking at a quiet low. We use the same technique in looking at the noise on this board as the others, a quiet low and a quiet high. And then here's what the quiet low noise is. This is 800 millivolts of noise on a quiet low with 3 of the guys switching. And you can see that signature. When the trigger turns off, we get a positive pulse. When it turns off, you get a positive. When it turns on, you get the large negative pulse there. So this is the kind of noise that you see on one of these boards in a really simple way. So this is the first measurement they do is they characterize the commercial board. Now, with what they've learned from that, and here it is for the quiet high, see the voltage drop on the power rail when it switches. Again, we're talking about 700 millivolts peak-to-peak noise on the power rail when the I/O switch, on the die, on the microcontroller itself. So this is the first measurement they do, and they look at the board and they looked at how can I make this better? How can I apply the principles of good routing for control path and for power distribution? How can I apply those in order to minimize the noise on the board? And so the other cool thing they can see also is if you slow down the sweep on the scope, look for longer time scale, you can actually see the clock noise on the die that's switching. It's the I/O rails and the core share the same power rail, and so when the I/Os are not switching, you're seeing the noise on the core itself as you have background operations, watchdog timers, and other counters going, so there's core operation. You can actually see the 16 megahertz. Actually, you get noise on both edges of the clock, so you see the switching of the clock on both edges in between when the I/O isn't switching. So you can get a good measure of the noise going on the die with this simple measurement method. Well, my students then take what they've learned in what not to do as an example in the Arduino board, and they redesign it. So they start with the schematic. They use standard, they take responsibility for it, I hope, and they may look at reference designs, but I try to instill in the sense of be careful. It might have been a dog that designed that schematic, so you want to still own the design yourself. So they take the design, they do the design, they turn that into layout, applying the good design principles. We get the boards fabbed. they assemble them and they test them. And I just have one example here to share with you of what the performance looks like when they're done. So this is looking again at quiet high and quiet low lines. And in this particular, I just grabbed this from one of my students' papers from last semester. And you can see the clock noise that's switching there. And then the peaks, that's when you have 3 IOs switching, just like when they set it up to measure from the Arduino board itself. Now this is on their board, and you can see the noise that they see switching. We're talking about 20 millivolts. What is that? 100 millivolts. So we're talking about 100 millivolts of noise on the quiet high, and on the quiet low, we're talking about like 120 millivolts of noise. So a significant reduction in the amount of noise that they measure on the Arduino board after applying good design principles. There's no cost adder to it. It's not we're adding a bunch of other components, changing anything around. All we're doing is good layout in order to translate the schematic into the physical design of the artwork. So it's an example of what we can gain in performance. Now you can say, well, who cares? After all, there are more than 1 million of these boards out there. Most of them are working most of the time. Do you really need to improve it? And part of that goes back to this idea of habits, that I think that regardless of whether the product needs it, if it's free, it's an important habit to get used to so that in the next design that you do, you're using the best design habits, best design practices in order to minimize this sort of noise. So I wanted to give you a little sense of what I'm working on now, how I'm trying to translate what I have been spending the years teaching practicing engineers, what I think is important to train students so that when they become practicing engineers, I don't have to go out and train them. And again, here are those 6 broad-based skills that I think are really important. I would love to get your feedback on it, so grab me sometime or send me an email. Let me know if you think there are other things that I'm missing or some of these aren't so important for you. And with that, I want to thank you all very much for coming out here and joining me today, and look forward to chatting with you after the sessions here. Thank you.
Thank you very much, Eric. I've got a gift for you. Remember backstage we were talking about your Steve Jobs uniform here? And look, this is about connecting with people, and we have Judy. I think most of you, or a good portion of you guys know Judy. So she thinks of these little things, and we've got Eric a gift for his presentation that is referencing his talk today. So thank you very much, Eric.
Thank you.
Appreciate it. Actually, if I could, just one more thing. One of the big themes we do here is this learn, right? Learn, connect, be inspired. Learn, connect, be inspired. And we really, really, really try hard to stay true to that. And that's why you don't see a lot of sales pitching going on here at AltiumLive. But this learn bit, I think I've really come around to, this industry attracts lifelong learners. And that's why you're all here, right? And Eric clearly is a lifelong learner, but more importantly, he's a lifelong teacher. Right? And if we look around the room, there was an article written last year about AltiumLive. They said, well, where's all the young people in this industry? Well, they're at AltiumLive. It's true. And some of us are older, too. But Eric's actually traveled with 6 of his students. And I just think that's a remarkable thing, right? So on the shoulders of all of us come the next generation, and Eric is a huge part of that. So thank you very much.
Thank you.
Thanks. All right, now we do some housekeeping. So first of all, look, full schedule, quite full schedule, and so we just really ask that everybody do your best to stay on time, and thus far, the past 2 years, everybody's done so. So if you could, just please be your best to be where we need to be when we need to be it so we can get to everything. Do want to say thank you to our sponsors. I think if you've been here before, you would notice that the sponsor alley is quite a bit more robust than it has been in the past. And those folks are attracted here because it's a very intimate gathering. This is not a trade show, and they find value in connecting with all of you guys. And I do encourage you all to visit the sponsors. because they do, in fact, make this happen. And this year, in a much bigger way than in the previous 2 years. Specifically, our platinum and gold sponsors, although they're all fabulous people. Those two guys, our diamond sponsor is Sierra Circuits, and our gold sponsor is Tempo Automation. Interesting, I just realized they're competing with each other. But those two sponsors have a raffle. So you get a shot at winning a Mavic Pro, or I guess, if you win both, a Hero 7 GoPro camera. So please visit our sponsors. Upstairs we have Altium Alley. So that's where you can go and interact with all of our products. We have demo stations just like we've had in years past. All of our experts are up there. Go there and ask them any question you want. Get a look at the products and see what we're cooking for all of you guys in the near future. We'll do the keynote around what's coming in 2020 tomorrow in the afternoon. Also up there, now this is something we conceived last year, and I felt a little awkward about it, but it turned out to be an excellent thing, and that's the Altium store. Okay, so there you can go buy some swag. We got t-shirts, we got the backpacks were exceedingly popular last year. But all those proceeds are part of our pay it forward effort, so we keep none of that money. We totally give that money away. And this year, no different, and we'll be giving that money away at dinner, which I'll get to dinner in just a second. Actually, I think that's the next on my bullet list. Dinner. You'd be a fool not to go to dinner, okay? This is a hallmark of the event, so much so that we try to change it. We think about every year, we brainstorm for months on how we do something different, and we just can't do it, okay? It's bigger and better, however, so if you've had the experience, you should do it again, okay? This event is unique in that 99% of you will actually stay through dinner, okay? If you're thinking about not going to dinner, I know San Diego's beautiful, the skyline's right there, and it is a great place. Save it for tomorrow. If you didn't book your tickets to leave on Sunday, well, that's your problem. Come to dinner, okay? Come to dinner. You will not regret it. That really is where that connection stuff that we talk about happens. You will meet lifelong friends there, I promise you. At least I have. And I'm to remind everybody that it's a 15-minute break, and then you're going to your technical sessions. So we now have a 15-minute break, and you go to your technical sessions. Thank you very much.
Tony has just finished, and we've got all of the layers down on the bottom row of tabs. We can also turn this into 3D and view completely 3D in the browser as well. And this works pretty awesomely, super fast. So again, access to design data anywhere you like. If you just go back to 2D mode as well quickly, Ben, one of the things that I want to explain here is that as well as just as viewing stuff, we can also place comments here. So what we're going to do now is just quickly dump a comment in here. If we go to the toolbar at the top, Ben, just underneath the bomb, and select the one in the middle, and then let's just select an area of this board somewhere, and then enter a comment in. So we can just put something in here like, come and take a look at this, or whatever you want to say to someone in it. We're then going to click the post. And this is going to put the comment onto the design. And what we're going to do real quick is just going to flick back to Altium Designer now. And we're going to switch back into 2D mode and go onto the comments panel in the bottom right. And we should now see our comment that we've just placed. So the cool thing about this is that whether you're inside Altium Designer, working in a browser on a mobile device or anything like that, you can effectively collaborate and communicate information in this very powerful kind of, what we call it contextual commenting. So you're effectively appending the comment to something visual, something that's meaningful. It's not just some abstract sentence in an email or something like that. Okay, so we've finished our design, and that's where the next scene will